Okay, we're going to start talking about shapes and polarity and all that good stuff today. Sorry, writing an announcement right now. Announcing the plan test. Okay, let me go ahead and enlarge this here and try not to be distracted by that. So, when we're talking about molecular shapes, the reason that this is important is because it turns out, and this is especially important if you're thinking about going into any biological field, medical field, anything like that, the shapes of the molecules in the body have a lot to do with the way that they react. Okay, and so this is especially important in organic chemistry, which is why organic chemistry is actually a part of this unit that we're starting now. Because this kind of goes hand in hand with the idea of the shapes and the intermolecular forces and all that stuff. So it fits really nicely into this unit. But the shape of a molecule is important when we're talking about how reactive it is. And we did this last year, looking at the bonding and non-bonding electron pairs and figuring out the shapes of the molecules. Okay, so I'm going to go through this fairly fast because, again, we did this last year. Okay, so when determining the shape of a molecule, what we have to remember here is the idea of VSEPR, valence shell electron pair repulsion. And that just means that electrons are trying to orient themselves in such a way around the central atom that they get as far away from each other as possible. Okay, and so the example here with this nitrogen, it has 4 electron pairs around it, okay? And these electron pairs here are basically just trying to get as far away from each other as they possibly can. And so that's how we can predict the shape of this molecule, okay? And again, I gave you a sheet last year where if you had the number of domains, then you could know exactly what the shape was. Unfortunately, again this year, as with most things in AP Chemistry, they're not going to give you that sheet, so you've got to have this stuff memorized. You actually need to know it. Now, it's not that bad, so I think you guys will be okay there. But I did put all of these things on this note sheet, so that hopefully it will help you. So, let's see here. Let me just go through this. Electron pairs are electron domains, okay? Now the thing that you have to remember from last year, and this is important, when we're counting domains around the central atom, which is the central atom here, then what you basically have to do is you have to consider each of the bonds that are being formed, okay? And then the non-bonding pairs as well. So around this atom we have 4 domains. The double bond counts as 1 domain because that double bond has to stick together. So when it's trying to orient itself so that these 4 get as far away from each other as they possibly can, this one right here has to stay together, and so that counts only as 1 domain. Okay? And that's basically what I just said. They have to stay on the same side of the central atom, so they only count as 1 domain when we count them up. So this molecule has 4 electron domains. Okay. And this is talking about VSEPR, valence shell electron pair repulsion, which is what we just talked about. So it's basically showing here, if you have to think about this in 3 dimensions, okay? But if you've got a carbon atom right here, and it's got 4 chlorines around it, then the best way to get those as far apart as possible is a tetrahedral arrangement like this. And that gives each of these angles here 109.5 degrees. And it's hard to see when you're writing on 2-dimensional, a flat screen or flat piece of paper. But those are all 109.5 degrees. Okay, so here are the electron domain geometries. 4, 2 through 6 electron domains, and these are the ones that you're normally going to have. Okay, if you only have 2 domains around a central atom, then it's going to be linear. Okay, and that's like this one up at the top here. Okay, because the way that these 2 domains can get as far away from each other as possible is to be on opposite sides of the atom, so that would be linear. If you have 3 domains, the way that they get as far away from each other as possible is a trigonal planar arrangement. 4 domains is going to be tetrahedral. 5 domains is going to be trigonal bipyramidal. And 6 domains is going to be octahedral. Okay. Now the trigonal bipyramidal is a little bit strange because it actually, the bond angles are not all the same. You've got 3 that are 90-degree angles, or I'm sorry, the 3 that are 120-degree angles, and then 2, the ones on top and bottom, that are 90-degree angles to the others. That turns out to be the most stable arrangement for that particular molecule. Okay? So all you have to do is draw a Lewis structure here, count the number of electron domains, and that's going to give you the shape of your molecule. Okay? Now, this gets a little more tricky when you have lone pairs of electrons, because then you have to remember other things about the shapes, but that's the main idea. Did I have octahedral back here? Okay, I just didn't talk about it. Okay, so let's take a look at a couple of these here. I do not have a lot of examples here. Okay, it's coming up. We just have to talk about all this stuff first. Okay, so again, the electron domain geometry is not always the shape of the molecule, and that's because of the lone pairs. All right, so for example here, this NH3 has, you know, 1 lone pair, and so really this is we would think of this as a tetrahedral arrangement, but because there's no atom up here, it's not really tetrahedral. This is trigonal pyramidal, because we've just got the 3 hydrogens that are being pushed down by the lone electron pair that's up here. Okay. Let's see. So the non-bonding pairs, that's what I just said. The lone pairs of electrons, those don't count for the shape of the molecule, just the atoms. Okay. So within each electron domain, there are different possibilities for the geometry. Okay. So you've got tetrahedral here. If you've got 4 actual atoms around the central atom, then that would count as tetrahedral. Now if you have 1 lone pair, like NH3, that's going to be trigonal pyramidal. Okay, and then you could also have 2 lone pairs here, and if you have that, then you're going to have a bent structure like water. Okay, now those bond angles are all going to be fairly close to 109.5, but not exactly. Okay. So in the second domain, there's only one possible geometry, that is linear. Okay. And another thing you have to think about here, if we just have 2 atoms in the molecule, there really is no central atom. So something like HF, something like that, where you, or you know, CO, carbon monoxide, anything like that, it's going to be linear. It can't be anything but linear, because you're just drawing, you know, you've got 1 bond there, and it's going to be a straight line. Okay, and so we don't really even think about those that much, because when you have just 2 atoms in the molecule, it's going to be linear. Okay, so for the third electron domain here, where are we at? The trigonal planar electron domain. There are 2 possible geometries there. Okay, one is trigonal planar, and if we have a lone pair, then we can have a bent structure. Okay, and so an example of that is NO2, NO2 minus. Okay, and again, see the way that they have that written. But this is really a resonance structure, so technically this is you've got a 1.5 bond on each of those NO bonds. Okay, just a little review there. Now here's the thing about, I'm not sure why this is stuck in the middle here, but let's go ahead and talk about this now. Because if we go back over here, turns out all of these angles are 120 degrees. Okay, when you've got 3 atoms in there, everything's equal, right? These are all atom B, whatever B is. So these are all 120 degrees. Well, it turns out that the lone pairs actually repel a little bit more than the electrons that are in the bonds. Okay, they're by themselves, they're just a little bit more repulsive. Okay, and so that actually bends this angle right here to be a little bit smaller than 120 degrees. Okay, it's going to be less than 120 degrees. Okay, and you don't necessarily need to know exactly what it is, But you do need to know how those lone pairs change the geometry just a little bit, change those bond angles. Okay, and so the idea there is this lone pair, it's kind of pushing on both of these bonds and forcing them down just a little bit more, so that we have less than a 120-degree angle there. Okay, and that's what this is talking about. Non-bonding pairs, they're actually physically larger. Their orbitals are actually physically larger. Okay, and so when you've got a tetrahedral arrangement like this, CH4, each of those is going to be 109.5. Okay, but then when you've got something like NH3 where you have a non-bonding pair, that's going to push down a little bit more on each of these bonds. Okay, and it's going to make the bond between the hydrogens 107 degrees instead of 109.5. So not a big difference, but a little difference. Okay, but then you get something like water, and you've got two lone electron pairs on the water. Okay, that's really going to push on this bond angle right here and force it together, and so now we've got a 104.5 degree angle instead. Okay, so you just need to understand what you really need to know is you need to know the bond angles of the major geometries, and then you need to know how the non-bonding pairs, the lone pairs, are going to change that bond angle just a little bit. Okay. Now we need to talk about double and triple bonds as well there, okay? Because that does the same thing. Double and triple bonds are going to place more electrons on one side of the atom, okay? And so that's actually going to cause those electrons to push a little bit harder on some of the other bonds, okay? So you've got more electrons here in this double bond. That's pushing these bonds a little bit closer to one another, so you end up with a 101.4 degree angle here and 124.3 degree angle on each of the CLC bonds, CLCO bonds, or angles. That probably didn't make a lot of sense. This angle right here, okay, and this angle right here are going to be bigger because of the extra electron density on that side due to the double bond. Okay, so you just got to keep that in mind. There's a couple of things that really do sort of influence these bond angles a little bit, and they will ask you questions every once in a while on the AP exam that have to do with why is this angle not exactly 120 degrees? Why is this angle not exactly 109.5 degrees? That sort of thing. Okay, you just have to keep that in mind. All right, getting back to our domains here. So now we've got the tetrahedral domain, okay, and the tetrahedral domain, again, if you've got all four atoms, that's going to be tetrahedral. If you have one lone pair, it's trigonal pyramidal, and if you have two lone pairs, it's going to be bent. We already talked about that, so I don't think I need to go into any more detail on that one. The trigonal bipyramidal electron domain. So here's where we're going to talk a little bit about why you've got the axial versus the equatorial positions here, okay? So you've got an axial bond, you've got an equatorial bond. These three right here are on the equator, okay? These two right here are axial. Axial are up and down, the equatorial are horizontal, they're on the equator. So those are the two distinct positions in this geometry, okay? And the reason that it forms that way, the reason that you have electron pairs forming the way that they do, and therefore forming the shapes that we do on these, is because of just the energy that results from putting the lone pairs in one place versus putting them in another place. So if you think about this for a second, let's say that in this SF4, I'm not going to be able to draw this very well. Let me see if I can use one of the pictures that's already here. So we've got SF4. Let's say that we put the other F out here, okay, and this was our lone pair instead, okay? So if you think about that, that lone pair is now at a 90-degree angle to three. It's at a 90-degree angle to three of these bonds right here, okay? So these are all 90-degree angles, right? Now, if the lone pair goes here, then it's actually only at 90-degree angles to two things, the ones that are up and down, the ones in the axial positions, and then it's got a 120-degree angle with the other two, okay? And remember, the lone pairs actually, they need more space, they take up more room, so it makes more sense for the lone pairs to go in the equatorial position rather than in the axial position, okay? And so that's why these form the shapes that they do, instead of, you know, one of the lone pairs going on top and one of the lone pairs going on bottom. And that, you know, it sort of would make sense to think about it that way, but that's not actually the way that this occurs, okay? And so what happens here, and this is the one that I did not give you pictures for on your notes, and I wish that I had. But you've got trigonal bipyramidal, and what you have to think about here is just where these things are going to go, okay? So you can have a trigonal bipyramidal arrangement, and that's this one right here, okay? No, I'm sorry. Trigonal bipyramidal is when it's, you know, when they're all atoms, okay? So you've got the three in the middle, and we've got an electron domain picture like that, okay? But you can also have a seesaw. This is the seesaw right here, okay? And that's if you have one lone pair, okay? Now, if you just imagine taking another one of these off here, okay? If we have two lone pairs, then you have a T-shaped structure, okay? So hopefully you can sort of visualize that. And then if we take off this last one here, if this is also a lone pair, then you just end up with a completely linear structure, okay? And so that's how the shapes for the trigonal bipyramidal work, and that's why they work the way that they do. Because you might think, just based on the way that this works, you might think that, okay, this one and this one, that's where the lone pairs would go, and then we'd end up with something that's trigonal planar, okay? But it doesn't work that way, again, because the lone pairs want to try and get as far away from everything else as they possibly can, and the best way for them to do that is to be in the equatorial position, horizontal rather than in the axial position, okay? And then we've got the, and again, this is the one that I wish that I'd put in your notes. It's not in there, so you may have to draw your own pictures on this one. But there you've got the trigonal bipyramidal, the seesaw, the T-shaped, and the linear, okay, based on how many lone pairs that you have, okay? And you do kind of need to know these. So maybe I'll get you another sheet that just has a breakdown of all of these. That way you can just have something to look off of and study for that. Okay, and then the octahedral domain, there's really three possibilities there. You can either have the full octahedral, where you've got 6 atoms around the central atom, okay, and the only way that's going to work is if you have an expanded octet. But that's true for each of the last 2 types of electron domains, actually. You can also have square pyramidal if you have a lone pair on the bottom here, so you've got your pyramid base, and this all goes up to a point here, so it looks like a square pyramid. And then you've got square planar, where you've got 2 lone pairs, and then you've got all 4 of your atoms in a plane, okay? And so that's how that works. We just talked about all those. Okay, in larger molecules, when you're trying to figure out the shapes of the larger molecules, it makes more sense to talk about, rather than talk about the geometry of the whole molecule. That gets kind of confusing because these things are bent and twisted all kinds of different directions based on each individual central atom. It makes more sense to separate each central atom individually and talk about the shape that each of those is going to have, okay? So here we really have 3 central atoms. 3 that are attached to several different things as opposed to just being an outer atom. And so this first carbon right here, it has 4 bonds around it, 4 bonding domains. So that's going to make it tetrahedral, okay? That's going to be its geometry. The second carbon here, it has 3 bonding domains, okay, and none that are non-bonding. So that's going to be trigonal planar. And then this last one here, it has 2 bonding domains and 2 non-bonding domains. So that's going to be tetrahedral overall, but really what that's going to look like is going to look like a bent shape, okay? Because two of those are lone pairs. And so, again, the predicted bond angles there, 109.5 on that last one, and 120 on this one. But we know that's not entirely true because this double bond right here is actually going to push down. I've got too many arrows here. Let me erase some of this. Okay, so this double bond here is going to push down on these. And so this bond right here is going to be a little bit less than 120. Okay, and then same thing, there's two lone pairs here, so those are going to push on the 109.5, and so this is actually going to be less than 109.5 for two of the angles, and then two of the angles are going to be greater than 109.5. Okay? And again, another reason that we want to look at the geometry here in this way is because this really, when these things react, they react in one place usually, and so it makes more sense to just think about, okay, what's the geometry around each of the central atoms, because those are the places it's going to react. So this gives you a good idea of what the actual overall shape of this molecule would look like. This is tetrahedral, this is your trigonal planar, and then this is your bent structure. Okay, and so overall that's kind of what that molecule is going to look like. So that's how we figure out the shapes of these things, is just taking the central atoms one by one and figuring them out. Okay, alright, let's see if we can do some of these. So we're going to use the VSEPR model to predict the molecular geometries of O3 and SNCl3. I don't know why I wrote O3, I already have it up there. Okay, so we've got oxygen, oxygen, oxygen. Alright, and we need to figure out how many valence electrons we have here, total of 18. I just used up 4 of them for these bonds, so that's going to be 14 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, looks like this one is probably going to be a resonance. Okay, so we're going to have to take 2 of the electron pairs here on one of the oxygens and swing them into the middle in order to make that central oxygen happy. Let me see if I can do this without erasing anything else. There we go. So it's going to look like this. That's actually a resonance structure, so we'd have to draw both. But for the geometry of this thing, we don't have to draw both of them. It doesn't really matter as much. What we've got here is 1, 2, 3 domains around the central atom. Here's a domain. Here's a domain, here's a domain. Okay, 3 domains around the central atom, and one of them is a lone pair. So 3 domains around the central atom is going to be trigonal planar. Okay, but because one of them is a lone pair, we only have 2 bonding domains. This is going to be a bent structure. Okay, so that's that one. The SNCl3, we've got 10 in the middle, SNCl3 minus. And this is a little bit weird because typically we're not used to seeing a metal and a non-metal combining in this way, but that's how this one works. So SNCl3 with a minus, and so the total number of valence electrons here, 10 has 4, each of the chlorines has 7, so 25 plus the 1 here, so 26 electrons. We just used up 6 of them the bonds, so we got 20 left. 1, 2, 3, 4, 5, 6, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, and then don't forget, when you get done with this thing, you got to put it in brackets and put the minus on the outside because this is a polyatomic ion. So it looks like here everything's fairly happy with this arrangement. What we've got here is 1, 2, 3, 4 total domains, okay, which would be a tetrahedral structure, but because one of them is non-bonding, then that's going to be a trigonal pyramidal, okay? So the actual geometry here is trigonal pyramidal. Hopefully this is all coming back to you guys as we go through this. Okay, so SF4 and IF5, we're still just predicting geometries here. So we got F, 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 F. Okay, and so on this one we've got a total of 28 plus the 6, so 34 total electrons here, valence electrons. We just used up 8 of them. So that's going to leave us with 26. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Well, we still have some electrons left over. Okay, and hopefully you remember this from last unit and from last year. When that happens, we can actually put them around the central atom as long as it's in group 3 or below. And sulfur is, so we can expand its octet, give it 2 extra electrons here. All right. So now, if we count around the central atom, we've got 5 domains, which is trigonal pyramidal. Okay, but 4 of them, sorry, are bonding, and 1 of them is not. Okay, so this isn't trigonal pyramidal. This is actually going to be seesaw. I just think it's kind of funny that that's an actual geometry in chemistry, seesaw. IF5, last one here. Okay, so IF5, we need to count up our valence electrons here. We've basically got 6 halogens in this one, so we've got 42 total electrons, because each of them has 7. We used up 10 of those with the bonds in the middle. 32 left. 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30. And iodine is far enough down we can expand its octet for those last 2. So we put 2 around the central atom. That gives us 32 total. And so what we have here is we have 6 around the central atom, which gives us an octahedral arrangement. But because one of those is a lone pair, this is square pyramidal. All right. So this one we're just looking at the way that this is written, and we're predicting the angles here. Okay, and so they want the HOC angle, so this one right here. So oxygen is our central atom there, and the OCC angle, so this is our central atom on that one. And we're predicting the bond angles there. Okay, so if we're predicting this, this oxygen right here, again, it's a tetrahedral arrangement. We've really talked about this already, with 2 lone pairs. Okay, and so the HOC bond angle here, when we look at that one, the lone pairs are really going to be pushing that a little bit closer together. And you sort of have to think about this in 3 dimensions. This is tetrahedral, okay? But 2 of those are lone pairs, so they're pushing that HOC bond closer together. So the HOC bond is going to be less than 109.5, okay? Because in a tetrahedral, in a true tetrahedral, they're all going to be exactly 109.5, okay? And then the OCC bond angle on this one. So we have to think about what angle that would form. And typically, this one, because it's got 3 domains around it, it'd be 120 degrees exactly, okay? But if we're thinking about that geometry, this actual angle right here, because of the double bond that's right there, it's actually going to be a little bit greater than 120 degrees. Because there's a greater electron density because of these this double bond right here. Okay, and so that's the angles that we would predict on that one. All right, now we're going to talk about polarity. Still had some writing on here from last year. Hopefully not too much. Okay, so I'm going to go through this fairly quickly, the polarity stuff, because basically what you have to remember with the polarity is you have to think about the overall dipole. And the biggest thing on this is just symmetry. You have to think about, is it symmetrical or is it not? Okay? And that's going to be your biggest clue as to whether this is actually polar or nonpolar. Okay? So we talked a little bit about polar and nonpolar in the last unit. The thing that really affects that is the electronegativity of the atoms. Okay? So an example here of something that's nonpolar is this carbon dioxide. Because if you've got this carbon dioxide bond here, okay, And if you think about this, the oxygen really is pulling the electrons closer to itself because it's more electronegative. But this is a perfectly linear molecule. It's completely symmetrical, right? So the oxygens are each pulling with exactly the same force on the electrons on each side of the carbon. That means you have an overall negative dipole on one side, overall negative dipole on the other side, and those sort of end up canceling each other out, okay? And so as long as this is symmetrical, your overall dipole moment, or your overall polarity of the molecule, is 0 or non-polar, okay? And so it's not going to have an overall charge because these are sort of canceling each other out, okay? Now if you got something like water, okay, water is going to be polar, okay, and again, the reason for that is because of the shape of the molecule. This is not symmetrical because we've got lone pairs here, right, that are pushing these hydrogens down, okay? And so when the oxygen pulls the electrons in the bonds closer to itself, that gives this an overall negative charge, and it gives the hydrogens an overall positive charge, okay? Which means that these things don't cancel each other out, okay? You've got one side of this molecule that's negatively charged, and you've got one side of this molecule that's a little bit more positive, okay? And that makes the overall dipole not 0. It makes it a polar molecule, okay? That's why water is so polar. Okay, so what you've got to think about here, when you're thinking about the different shapes and all of that stuff, you want to think about, are these things symmetrical or not, okay? And that's going to be a really big deal as far as figuring out whether it's polar or non-polar, okay? So you look at this HCl right here, okay? Obviously not symmetrical. The chlorine's going to pull the electrons away from the hydrogen. That gives this an overall negative and an overall positive dipole, okay? So there is a negative and a positive end to that molecule. If you look at something like NH3, again, you've got a lone pair up here, okay? So the nitrogen is pulling the hydrogens closer to itself. It's pulling the electrons closer to itself, away from the hydrogen, okay? And that gives this an overall partial negative charge and then a partial positive on each of these hydrogens. Because it's not symmetrical, one part of that molecule is going to be positive and one part is going to be negative. Now with the carbon tetrachloride here, these are all 109.5 degree angles, okay? And so the chlorines are pulling the electrons away at exactly opposite angles, and this overall, because it's a symmetrical molecule, ends up canceling out, and so this is non-polar, okay? The BF3 down here, same thing. The fluorines are all pulling the electrons out away from the boron, but because it's symmetrical, then the dipoles end up canceling each other out, and overall it's non-polar, okay? And then you can see here, this is a tetrahedral. So if we had one more hydrogen up here instead of a chlorine, this would be a non-polar molecule. But because there's a chlorine there instead, that's going to make it polar, okay? Because now we have an overall negative on this chlorine, and that makes the rest of the atom just a little bit, or the rest of the molecule a little bit positive. Okay, so that's how the polarity thing works. Now, see, I already have these all written. I'm going to pause this for a second while I erase those, because I don't want that on there. So hang on just one second, bear with me. Okay, sorry about that. I just didn't want these up here. I wanted you to actually see these getting created. So first one here is BrCl, okay? And that one actually, that's just a linear molecule, because we just got two things there, all right? So what we've got to think about on that one, Br bonded to Cl. First of all, we got to think about trends to figure out which one of those is more electronegative. And because the chlorine is smaller, that means that its valence electrons are a little bit closer to the nucleus. So it's actually able to pull electrons towards itself a little bit more because there's less of a shielding effect going on there. And so the chlorine is going to be able to pull the electrons a little bit closer to itself. So overall, there's going to be a little bit of a partial negative here on this side of the molecule and a partial positive on that side, which makes it polar. It is not symmetrical because there's two different types of atoms there. Okay, SO2. So we've got to draw out the shape for this one. So this one, we've got, let's see, 18 electrons minus 4 gives us 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, again, we've got a resonance structure here where one of these oxygens is going to give one of its lone pairs in here so that a double bond can be formed. Okay? So, if we're looking at this, basically we have 3 domains around the central atom, and one of those domains is a lone pair. This molecule does not look very symmetrical, right? And so, let me just make sure I counted that right. 18. Yeah, we have 4. Okay, yeah, that's right. So, because this has a lone pair, and the lone pair a lot of times is a big red flag. Not always, but a lot of times that's a big red flag that you're going to have a non-symmetrical molecule, okay? So because this is non-symmetrical, because it's going to actually have a bent structure to it, or a bent shape, that's going to be polar as well. SF6. Not sure if we just did this one or not. 3, 4, 5, 6. Okay, and so we've got 42, 48 electrons there. We just used up 12 of them with the bonds in the middle. So that leaves us with 36 electrons. And if you think about that, you've got 6 outer electrons. You put 6 around each of those. That uses up all 36, okay? So you can put the dots around all the fluorines. I'm not going to do that right now. But the basic idea here is this is an octahedral. Okay, because this is octahedral, you're going to end up with a symmetrical molecule, okay? It's all the bond angles are the same, 90 degrees, and so this one is actually going to be nonpolar. Alright, so really the big question you got to ask yourself on these is symmetry versus not symmetry, okay? And then the last question here, which of these has the largest dipole moment? Okay, so if we take a look at these, H2O2, it's actually going to look like this. And again, you might not have exactly known that. Not a big deal if you didn't. So when we draw the structure of this one, we've got, let's see, 14 valence electrons, if I'm doing my math right. We just used up 6 of those. We've got 8 left. And hydrogen does not want any more valence electrons, so those are going to go around the central atoms. Okay? So what we have here is a couple of bent structures, alright? So that one is not going to be symmetrical overall. So we'll come back to that one in just a minute, okay? The HCl, again, overall dipole. So that one looks like it would have a fairly large dipole moment as well. The SO2, we just did that one. Okay, that one's also a bent structure. The NO, not going to have that much of a dipole because they're fairly close together on the periodic table. And then the N2, you got N and N on that one. And so what you're going to end up with here, I think I'm missing something on this one. Hang on just a second. Okay, sorry about that. My gut was telling me it was the HCl on that one, but I wanted to be able to explain why the H2O2 is not. So we talked about the fact that this is bent, so really we're going to kind of write this like this. Okay, that's how that one's going to look. And so if the oxygen's pulling the electrons, well, okay, sorry, that's not happening. These oxygens are symmetrical as far as their electronegativities, okay? But notice that's sort of pulling in opposite directions, so actually the fact that this is bent in 2 different ways is going to end up helping to cancel out the dipole, okay? And so that one's going to be less polar because of that. Okay, so hopefully that makes sense. So the one that actually ends up having the largest dipole moment out of all of these is the HCl. If you look at the rest of these just based on where they are on the periodic table, the rest of them are a lot closer together. The SO2, the NO, and the N2. Obviously N2 is not going to be polar at all. Okay, but the reason it's not that H2O2, which that's kind of, I pulled this as an AP question. It's kind of a nasty question. But the reason the H2O2 isn't is because if you think about the fact that it's bent in two different ways there, then thinking about the geometry on that one, those two dipoles end up canceling out. Okay. All right, so that's the idea behind the polarity and the Lewis structures. I know that was a long one. I think you guys remember most of that stuff, though. There's really not a lot of new stuff there, so hopefully that all made sense, and we'll see you in class.